So we mute ourselves and turn the video off, right? Until
It's okay. You know, it's up to you.
No. It's up to you. Yeah. Mhm. Yes.
Oh, okay. Hi. Good morning, good afternoon, good evening, everyone. Depending on where you are. So I'm Kong, and let me just try to do a quick update of the Jumina session. Yep. So I think we are in our 6th Jumina session. Thank you for staying with us for all this time. And just a quick update. So last week, we had we broke our record. We have 381 concurrent viewers and 432 unique viewers last week. So it was just very good. We were all surprised. And for the mailing list wise, we have 450 people subscribed to our mailing list. For people who are seeing this for the first time, I would like to encourage you to sign up to our mailing list, because this is the main and official way of distributing the announcement. And sometimes I would send out a reminder email, or if there's additional document or PowerPoint the speakers would like to share with you. This is this is the main channel of how we will let you know. And also, the recordings for previous sessions from the 1st until the 5th session, if the speakers allow us to post it on the website, we have all the videos posted on the website. So feel free to check out. And also for the people who are watching this for the first time, as usual, use the Q&A to ask questions if possible. You can vote on it and answer it and comment on it if you want. And you can type your questions anytime throughout the entire session, even when the presenter is also presenting. And if you are otherwise, if you are new or you're not familiar with the Zoom interface, feel free to raise your hand. Or if you think that I'm not conveying your questions very correctly, or if you have like further points you would like to elaborate on your questions, feel free to raise your hand. We will allow you to talk and you can ask verbally. And finally, like do not type your questions on in the chat room. You can use the chat to say hi and do whatever you want, but don't type your questions don't type your questions in the chat, because like most likely I will not be able to see it. All right, so I will pass the session to Bob, and then he will introduce our speakers today.
Okay, so today we have two very interesting and exciting talks for you to listen to. The first one is from Lyon, and Quentin is going to tell us about dissolution DNP. And the second talk will be from Tatiana Polanova at University of Delaware. And she will be talking about magic angle spinning DNP experiments on a variety of different and exciting biological systems. So Quentin, why don't you take control of the Zoom floor and start your presentation.
Thank you, Bob, for the introduction. And thank you to both of you for this wonderful opportunity to share a little bit about my work on spin diffusion barrier. Today, I would like to show you a method that we have developed to study the flow of polarization from nuclei close to the electron to nuclei that we can observe in the bulk in the context of dissolution DNP experiments. So, I'm part of Samy Janin's team in Lyon. I'm a PhD student. And as I said, we work on dissolution DNP. So I'd just like to do a recap on what is dissolution DNP. So it consists in hyperpolarizing samples at low temperatures. In our case, we work between 1.2 and 4.2 Kelvin, and usually at a field of 7 Tesla. And once we have hyperpolarized our sample, we rapidly melt it using superheated water and transfer it to a spectrometer for liquid state detection. This was introduced in 2003 by Jan-Henrik Ardenkier-Larsen, and it showed to enhance the signal in the liquid state by many orders of magnitude. And today I will only talk about the solid state part of the dissolution DNP experiment. And the sample that I will use is always a typical DNP juice with temple as a polarizing agent, water as protons to polarize, and glycerol as a glass forming agent. The typical signals that we get are like this. So here this example is at 3.8 Kelvin, and we get a polarization of 39%. And as you see, the signals are broad because we are in static conditions. So here it's a 30 kilohertz broad signal. Here I show you two build-up curves at different temperatures at 1.2 Kelvin and 3.8. And what you can see is that you can go much higher in polarization at lower temperature, but it also goes slower. And if we play with temperature, we see that going lower in temperature, the DNP rate gets lower, but the polarization gets higher. So there is clearly an advantage, but we have to pay the price of a slower experiment. And boosting the time, the rate of the DNP is important both for dissolution DNP and MAS DNP. The faster we can, the polarization buildups, the more we can repeat experiments. And there isn't a very clear explanation on the temperature dependence of this process. This is what we want to understand. Before I move on to other results, I would like to introduce a little bit of theory about the spin diffusion barrier. So let's call D the dipolar coupling between the protons in our sample, and A the hyperfine interaction between the proton and the electron spins. Diffusion barrier theory says that when the dipolar interaction between the protons is weaker than the hyperfine interaction, we can have no diffusion. So the nuclear spins that are close from the electron cannot exchange polarization. In particular, they cannot exchange polarization with the bulk spins, the one that we can observe. And this has strong application for DNP. because the hyperfine interaction is greatest at closest distance to the electron. So also the rate at which the electron can polarize the nuclei is greater at close distance. And diffusion is quenched by this diffusion barrier. So we have to rely on hyperfine interactions that are weaker and because they're longer range. The diffusion barrier is not in fact that clear cut, and there's a lot of literature about this. It's in fact a bit smoother, and that's I would like to go a little bit through the literature on this subject. Spin diffusion was first introduced by Blombergen in 1949. He used this concept to explain how paramagnetic impurities could relax indirectly spins that are far away in the bulk. In his model, he used a model where he described the polarization in time and space using a diffusion equation with a diffusion coefficient and a relaxation term. And he assumes that the diffusion rate is constant in space. Bloomberg refined the model by introducing the spin diffusion barrier, saying that it was zero within a certain radius. This concept was rapidly applied to DNP a few years after by Leibson and Jeffreys, and then Kuchishvili. And basically, the explanation is very similar. It's just that in this diffusion equation, you add a term that describes the polarization by the electron. And in the 70s, there were many articles showing that the rigid barrier is not an appropriate description. Here, I just cite two important ones, but there's a very broad literature in these days on this. And then more recently, here I just cite some examples of the modern literature, but there are few studies on samples in modern samples in amorphous solids. So there's a great need to understand in more detail how diffusion occurs in the samples that are of interest nowadays. And here, I would like to show you a first experiment, a simple one, done by Frédéric Mentink-Vigier in collaboration with us at the MagLab in Tallahassee. So here we simply do a saturation recovery in MAS conditions. And now we repeat the experiment, but before we do it, we do DNP. So the difference between the blue and the orange curve, both of them are saturation recovery experiments. But for the blue one, we have done a DNP buildup before, and then we have gated the microwaves. In principle, there should be no difference between the two curves, but we clearly see that the buildup behaves differently. So we interpret this as this memory of the system as the fact that the spins that are close from the electron are not affected by the saturation pulses. And this polarization will diffuse to the visible spin. And that's what I want to try to convince you in this presentation. And I said that there are spins that we can't see that are close from the electron. We can easily study to which extent the electron spins obscure our signal. And here I have recorded the signal intensity as a function of the electron concentration in the sample. As I said, we mainly use 50 millimolar radical concentration, which corresponds, as you see here, to approximately 25% of the signal being quenched. And this leads us to estimate that the spins that we don't see are within a radius of approximately 13 angstrom around the electron. And now what we want to do is to observe how polarization flows from this 25% to the spins that we can actually see. For this, we use the experiment that I presented in MAS. And here it will be the same, but in static DNP at lower temperatures. The experiment is simple. It consists in saturating the signal strongly. We make sure it's really zero. Then we perform DNP during some time, and then saturate again. So what happens here, I will represent the sequence of events with this sphere. So here we have no polarization, then the sample is polarized, and the saturation doesn't affect the whole sample. It only affects the spins that are, because the pulses have a limited bandwidth, the spins that are too coupled to electron are not affected by the saturation. So the polarization that remains near the electron diffuses to the spins that we can see. Now let's have a look at the results. This first curve is when the DNP delay is set to 0, so it's the normal saturation recovery. But as we increase the delay where we do DNP, we have an overshoot coming. This is why we have called our experiment the HypRes experiment for this hyperpolarization resurgence. So this tends to show that as we do more longer DNP, we polarize the core spins more, and then there will be a higher overshoot. You may notice that 5 seconds is very short for the DNP buildup in low temperature DNP, because our DNP rate is in the order of 40 seconds at this temperature. If we now wait until the DNP buildup is completed before doing the saturation, we have a very strong overshoot. It's approximately 25-fold the thermal equilibrium. And in all the experiments that I will show you from now on, I will subtract the thermal signal to this HypRes signal, so that we have a signal that is expressed as an excess of polarization with respect to thermal equilibrium. And now I start to play with temperature. So I repeat this experiment on a single sample, always polarizing the sample until I reach the DNP plateau, but I lower the temperature step by step. And what you can see is that the polarization excess reaches a higher overshoot as I decrease the temperature, which is expected because, as we have seen, going to lower temperature increases the steady state DNP polarization. So the polarization that remains among the core spins is higher at lower temperatures. But more interestingly, what we see is that the rate at which the polarization escapes the core spins decreases with decreasing temperature. For this, to understand this, we have, or to quantify this, we have developed a very simple two-reservoir model, where we assume that the spins that we can see, those that we can see, act as two reservoirs connected by a flow rate constant, and each reservoir has its own relaxation rate. We assume that the bulk spins relaxation is negligible in front of the core spins, so that they relax only through diffusion to the core spins. And we get this differential equation that describes the system. And the result of the model is this one. In blue is the bulk reservoir, is what you can observe, and in orange is the spins that you can't see. The rate at which they equilibrate is to a good approximation. It's the flow rate constant, and what you can see here is that they first equilibrate, and then as it relaxes to thermal equilibrium, the core reservoir drives the bulk reservoir also to thermal equilibrium. So I have applied this model to our curves as a function of temperature, and here's the result. Obviously, there's not a perfect fit between the model and the experiment, because we have simplified the geometry of the interaction greatly by saying it's simply two reservoirs. But it allows us, the beauty of this approach is that it allows us to extract a very simple parameter that describes the flow, as you can see here, and we say that it has the temperature greatly influences the diffusion between the two reservoirs. So it leads us to a few conclusions. First, there is polarization building up in this core reservoir. It can be shared with the bulk reservoir. Our method HypRes allows to detect this flow, and the flow rate is found to be highly dependent on temperature. Now I move on to a slightly more complex experiment where in the preparation step, I add an adiabatic inversion pulse. So let's go through the sequence again, and here what I show you is the polarization as a function of this offset of the protons. So in the beginning, we have zero polarization. After DNP, we have homogeneous polarization, or at least we assume that we have a homogeneous polarization throughout the sample. And then we invert using a broadband pulse. In the experiment that I will show you, I have used from 500 kilohertz to 4 megahertz inversion, centered on the on my NMR signal. And I take into account in this plot the fact that the inversion is not perfect, and it doesn't go all the way to 4 megahertz, for example, in this example. And then so these spins that are very far from the electron are not touched by the inversion. Some I inverted, but it depends on the width of the inversion. And finally, we saturate the spins using hard pulses, which have a very narrow bandwidth. This can be translated into a distance from the electron. So assuming that that the frequency of the spins of the nuclei is dominated by the hyperfine interaction, I get this distribution of polarization for the nuclei as a function of the inversion width. And here's the distance to the nuclei, to the electron. And here are the results for the same sample at 3.8 Kelvin. This is our starting point. We have saturated bulk spins, and the core spins are separated into two. The spins that are far from the electron in the core reservoir are inverted, and those that are closer to the electron remain positively polarized. What we observe is that the inverted spins rapidly exchange equilibrated polarization with the bulk spins, and then on a slower time scale, the non-inverted spin will give the positive polarization to the bulk spins, and finally they relax altogether to thermal equilibrium. So there are a few observations to do here. First, the more we invert, the stronger is the negative overshoot, as we can expect it, because we invert more spins, so we have more negative polarization. And consequently, also, the more we invert, the less the the smaller the positive overshoot, which is in agreement with what we can expect. Another interesting observation is that we estimate that the fact that the curve with an inversion of 3 megahertz and that with 4 megahertz to give different results mean that the spins that lie here still are in contact with the bulk. So this reduces the spin diffusion barrier in our case to less than 4 angstroms, which is one of the nice findings using this chirp inversion. And another interesting feature on this experiment, here I'm zooming on the part where the signal goes from negative to positive. And what we can see is that and be careful, it's here, it was a logarithmic scale before, and here it's linear. What you can see is that the wider the inversion, the weaker is the slope at which the polarization goes from negative to positive, which shows that when we invert spins closer to the electron, the diffusion rate for the polarization to get out of this layer gets weaker and weaker. So this experiment gives us insights into the into the diffusion rate as a given function to the electron. And to get numerical quantitative analysis of this, we hardly can use the reservoir approach that we used earlier. So this is where Arthur Pinon comes into play. We collaborate with him to explain these results using finite element simulation. So the approach is very similar to that of the 50s and 60s, where we use a diffusion equation to explain the data. But with our modern computers, we are not limited to analytically solvable equations, so we can use any diffusion coefficient that we want, which was a limiting factor in the early days. So here I will show you a video this will be the signal along time, and this is the signal in space. So this is the distance to the electron, and it will move with time. And the right panel is a zoom on this layer. So if I start the video, I need to remove the pointer. Yeah. So I start the video, and you see the polarization equilibrating. So you see that first the inverted spins give the polarization to the bulk, and then on a slower time scale, the non-inverted spins exchange the polarization. So let's have a look again. So this gives us a negative signal and then positive. And now I want to tell you a little bit about the parameters of this simulation. So in this model, we assume that the T1 is dominated by the fluctuation of the electron, and that the lattice vibrations are negligible. So we can just use the simple function that describes the relaxation as the or intrinsic relaxation from the distance to the electron. And this coefficient for diffusion is arbitrary. We have, Arthur has done some optimization to find some diffusion coefficient that would fit the data more or less. But the next step is to get an analytical expression for D as a function of space. And what I want to try is the model of electron-driven spin diffusion. So I want to calculate a curve for the diffusion using the electron-driven spin diffusion model. A few words about this. Already in the 70s, there were hints that the fluctuation of the electron can help to compensate for the mismatch in energy between the spins in the gradient of polarization of a magnetic field. And then it was more detail came with Demidov and Atsarkin in the 80s. And recently, Korzelius and his group showed experimentally in MAS conditions that this effect was efficient. And in our case, where we have a strong electron concentration and a lot of electron flip-flops, I believe that electron spin diffusion is likely to explain our results. And this coefficient will depend on the flip-flop rate of the electron, which in turn depends on temperature. So I hope that this approach can explain how temperature influences the diffusion in our experiments. And interestingly, Malcolm last week presented his approach with Lindblad theory and mentioned this paper by Karavanov and Kuchenberger, which uses Lindblad theory exactly to calculate this sort of diffusion in DNP experiments. So I think so. There's a still. I want to use this theory to explain this diffusion process. So finally, what I've shown here is that spins as close as 4 angstroms to the electron can share polarization with the bulk, and we don't find any evidence of any barrier in our conditions. And as I've said, I hope that our approach will finally lead to understand the temperature dependence of DNP. With this, I would like to thank the people who participated to this project with me. Of course, our collaborators, Frédéric and Arthur, and also people from Bruker who provide a lot of help. To mention only a few: Jim Kempf, Dimitri Yashenko, and Roberto Melzi. And also our funding agencies. And before finishing, I would like to announce an event that I'm taking part to. This is the first Zero to Ultra Low Field NMR conference that will take place online in September. I'm part of the European ZOLF network, so I hope to see many of you attending this conference. And now I'm ready to answer your questions.
All right, thank you, Quentin, for your very interesting presentation. But maybe just ask, like, is this is it free to attend the Zero Ultra Low Field NMR virtual conference, or is there a cost?
Yes, it is.
It is.
No, it's free.
Yeah, this is important.
Yeah. Thank you very much for asking. That's a good one.
Yeah. So like, thank you very much. So like, I would just ask ask a question, like, so that like you have time to type your questions, and also like you can vote on your question and stuff like that. So like maybe just I would just ask, like, so on slide 11 when you show like the resurgence hyperpolarization, I'm just curious. So like what is the contribution of the cross relaxation from other spins, other nuclei when you saturate the proton signal? You know, would you expect like, you know,
Slide 11.
yeah, something like that.
So yeah,
exactly. You know, like you have a spin reservoir from, I don't know, deuterium or carbon. When you saturate a proton reservoir, would you expect like the cross relaxation behavior, and how would it affect your data here?
Yeah, so to make sure that the effect is not due to electrons, we have also repeated the experiment using a fully protonated sample. And we see that we still have, when only the protons are present, we still see the effect.
Okay, thank you.
To answer, this is a first answer. And in fact, the MAS experiments to make sure of this were also performed in a fully protonated sample.
Okay, and then like I saw like someone raise like his or her hand. Sasar, would you like to talk now? You can unmute yourself. Sasar. Okay, while waiting for him or her to like figure out the technical part, let me just ask, like, so from the first question from Asif, in your experiment, how do you ensure that there's no crosstalk? Yeah, okay, this is like the same question that I asked.
Yeah.
Okay, and then like next question from Malcolm, what was the assumed form of the dependence of D from the distance from the electron? I assume D is the diffusion coefficient, and what's your justification for that form?
I guess
it's a Laurentian function, sorry.
I guess you talk about this one, and here there's absolutely no justification, only that we just want to try to see if we can find some curve that allows to fit the data. And for me, this justifies that to put the effort into trying to use analytical expressions. So there's no theoretical justification for now. Later on, my goal is really to have an analytical expression that is justified by itself.
Or maybe, Malcolm, you have something that you think you can justify it. If you're free to talk if you want.
No, thanks very much, Quentin. It was a lovely talk, and no, it was just curiosity, really. As you said, the spin diffusion coefficient must depend in a complicated way on T1 and hyperfine couplings, and yeah, I have no idea how you would estimate it. So I just thought maybe you had some insight into that.
Yeah, so the different papers that I mentioned here at the bottom give really interesting insights how the fluctuation of the electron can cause this, the first three at least.
Okay.
Okay, next question.
Thank you.
Okay, next question from Asif again. How does spin diffusion barrier depend on the concentration of radicals? Electron free from, I think you talked about this on the crosstalk, the flip-flop rate. Can you measure it? Or...
Yeah, so that's a really interesting question, and I'm happy that you ask it. So if we solve this, what I just mentioned to Malcolm now, and this would give us an explanation, because increasing the radical concentration will cause more stronger flip-flop rates. And so if the electron-driven spin diffusion is the answer, then this is likely to be the answer. But it's true that when we go to 25 millimolar radical concentration, we have slower DNP, and this could be part of the explanation.
Can you change like the rate by going to extremely low temperature? Or does...
yeah, so you mean the rates, the
crosstalk, the electron flip-flop? Oh.
Yes, I think we can, and I would like to measure the electron flip-flop rate as a function of temperature. For now, I don't have a precise measurement of this.
Okay. Anyway, next question from John. How is the spin diffusion described in terms of thermal diffusivity?
I must say, I don't really understand what you mean.
Maybe let me just allow him to talk. I assume it's something similar to what I just asked. I don't know. John?
Yeah, I mean, I guess basically the question that I had is, so you have some spin temperature in different places, and in general, you should have some thermal conductivity between these. Can you describe it in a simple way that way?
If I understand your question correctly, this is exactly what these equations does.
Yep.
I think so. I think it does. Otherwise, I haven't understood your question.
Okay, next question from Adam. Have you tried this on other narrow line radicals like, I don't know, Trito, BDPA, or?
Next week.
Next week, okay, perfect. And Nino has a question. What are T1 times of the electron at these temperatures? Seconds?
At 1.2 Kelvin and slightly lower field, 6.7 Tesla, it was measured to be 100 milliseconds. So, but it is granted to be strongly dependent on temperature. So if we go to 4 Kelvin, from 4 to 2, it will strongly depend because there's this 1 minus p square of the electron term. So I don't want to go too much into the details of this, but there's a very strong temperature dependence in this.
Okay, range. Yeah, I will just take one last question from Asif again. Will MS have a much shorter diffusion barrier since certain orientations, smaller hyperfine coupling can always diffuse out the polarization?
Yeah, so I'm sure Frédéric would
exactly. He answered that.
say a lot about this, but
maybe I will allow Frédéric to talk. That's easier. Fred, you want to talk?
Hi, do you hear me?
Yep, sure, we can.
Okay. Well, in principle, the MIS allows nuclei with different offsets to talk one another on a periodic fashion. So these are the rotor events. So in principle, the diffusion barrier, if we can call it a barrier, is actually smaller. Now, Frédéric Perras just published a paper where he showed that the structure of the radical may have also an influence on this. So he may have a specific answer.
Okay. Yeah, I think thank you for your questions and your answers. And if you have more questions, you can feel free to send contact and email, and he will answer. So I will pass the session to Bob, and then Bob can introduce our next speaker. Bob?
Okay, so our next speaker is Tatiana Polonova from the University of Delaware, and she's going to be telling us about magic ink.